Okay, so we're going to do today the lecture for chapter 12, which is on glaciers. So to start this off, this is kind of part of what we've been going over the last couple of lectures. I know it's been a couple of weeks, so we're going to have to work our way back into this. But we've been talking about basically the hydrologic cycle, the way water circulates through the environment of the Earth. We've talked about river systems, we've talked about groundwater. Now we're going to talk about glaciers. Glaciers make up a part of the hydrologic cycle known as the cryosphere, basically all the ice on the planet. After this, we'll talk about oceans and shoreline environments. So first and foremost, what is a glacier? Okay, well, it's part of two cycles. It's part of the rock cycle in that a glacier is a incredibly powerful way of breaking down and eroding rock. So it breaks down the material through abrasion and it transports the material. It's also part of the hydrologic cycle. Now, generally speaking, for our purposes, there are two types of glaciers. Okay, the first and foremost are the alpine glaciers. These are glaciers that are found in mountain areas. They occupy the valleys within mountain ranges. The other type of glacier is the continental glacier. These are large, massive ice sheets, sometimes over a mile thick, that spread out over the land. Generally speaking, the only ice sheets today exist on Greenland and Antarctica. They usually flow out in all directions. Best way to think about this is if you've made a pancake. When you pour the pancake batter into the pan, it spreads out in all directions. That's what a continental glacier does. And the reason it does this is that it's moving under the force of its own weight. So its own weight causes the material to move. Now, for other types of glaciers that the book mentions, there are things like ice caps, which are basically just smaller versions of ice sheets, basically less than 50,000 square kilometers in size. There's outlet glaciers there, and there are Piedmont glaciers, which are basically just types of valley glaciers and how they are exiting the valleys that they're within. We're not going to concern too much about this. Slightly more than 2% of the world's water, as we talked about with groundwater, is tied up, and river systems is tied up in the ice. So what would happen if that melts? Well, that's part of a problem I have in general with this discussion. 60 to 70% of all the world's ice is tied up in the Antarctic ice sheet. Cool. Some estimates say that if that melts, sea level will rise between 60 and 70 meters, 200 plus feet. That doesn't make a lot of mathematical sense to me because at the height of the last ice age, sea levels were anywhere between 200 and 400 feet lower than they are today, and there was about 20 times more ice on the planet. I have difficulty seeing how 1/20th the ice could actually cause the same increases as roughly 19/20ths at the low end. So take how much the ice can increase sea levels with a bit of a grain of salt, because I think there's some miscalculations going in, especially since some of the ice sheet in Antarctica is already floating, which means it's already displaced the water it would displace if it melted had it been on land. But that does not in any way, shape, or form take away from the fact that if all the ice on the Earth melted, sea levels would rise to some degree that would still be devastating for coastal communities. So, how do we form a glacier? What do we need? Well, that's something I want you to think about during the rest of this discussion. Not specifically the mechanics of how a glacier gets formed. We're going to talk about that in just a second. but what are the conditions on the planet? If I want to create an ice age, what are the conditions I need to start that? Because I think from a physical standpoint, we may think of it too simple. And I'll demonstrate that at the end of today. But visual aid, how do we get a glacier to form? First and foremost, what we're going to need is a location. And in this location, what we need is for it to snow. Now let's say it snows that deep during the course of the winter. Over the course of the summer, we need that snow to not completely melt away. This is the key. So maybe this ends up being the level of our snow. Now we do this year after year after year. Snow level year after year after year after year after year. This is what we call a snow field. Snowfields can be interesting in that they can actually set up their own weather conditions. The snow is white, it reflects light and heat away from it, actually causing the temperature above it to remain colder, helping to preserve it as long as it's pristine. If the snowfield gets dirty, it can attract heat and cause itself to actually heat up higher and melt faster. Now, basically speaking, once we start getting this pack developing, what's going to happen is we're going to start to see the characteristic of the snow change. At the top, it's still going to be its nice crystals, whatever it fell out as. When there's many different types of snow crystals. But as it piles up, the air is going to get forced out. And the grains are going to go from maybe being, a grain that's, I don't know. I know they're five-sided. They can be very elaborate, but let's just say a star pattern. Okay, it's going to go from that to something a little more compact. So the snow is going to compact, and we call that compacted snow firn. Kind of like little granules of snow. As the snow pile gets deeper and deeper still, that firn is going to pack closer and closer together, squeezing air out of it. Finally, when we get about 50 meters deep, we begin at the very bottom of the pile to form glacial ice. So we need at least 50 meters of snow to start to form glacial ice. So at least 150 feet of snow, 160 feet of snow, before we actually start seeing ice form. That's to start the ice. Now, in order to get the ice to move, we need a lot more. Okay? So, in order for the movement of the ice to happen, what we need, I gotta move things. The dog is bugging me. He wants up. In order for the ice to move, come on, Clay. There you go. In order for the ice to move, one of the things that we need to have is enough ice. Okay? So generally speaking, we have to get the ice thick enough so that we get into the different zones. Let's see. The whiteboard didn't come with an eraser, so I gotta makeshift something here. So I'm going to draw out basically a typical alpine glacier longitudinal cross section. In other words, a cross section down through the center of the. Okay, basically looks something like this. Generally speaking, you have a pile of material at the end. We'll talk about that in a little bit. The upper portion of a glacier, the top 50 meters or so, my 5 just looked like an 8, is what we call the zone of fracture. meaning that the ice is going to behave brittly. It's going to break, it's going to fracture. This can cause cracks to develop in the surface of the glacier that we call crevasses. These are very dangerous features on the glacier. You may have seen movies or documentaries where people are actually walking on glaciers. They're chained together or roped together, and they actually have a fair distance in between them. And the reason for this is these crevasses can be hidden. They can get snow that builds up on the top of them and creates what we call a ferry bridge. Part of the reason it's called a ferry bridge because only a ferry can walk across it because a ferry is light enough. A human steps on a ferry bridge, the bridge collapses, goes down into the crevasse. You go down into a crevasse, odds are you're not coming out unless you've got help that's there immediately. Otherwise, you're going to have a nice cold nap. But below the zone of fracture is the ductile zone. And again, that's about 50 meters deep to get to this plastic zone or ductile zone. And this is where where the ice, well, technically ice is a rock. I mean, technically it's a mineral. Below the fracture zone, we have plastic flow. So we're able to have the glacial ice move under its own weight. So it moves kind of like silly putty or Play-Doh or clay under pressure. It just kind of oozes to a degree. Now, oops, where did that, there it goes. Generally speaking, the rate at which a glacier moves can vary greatly. It depends on a large number of factors. Part of it's going to depend on, I got to figure out where to set this down at. Part of it's going to depend on how big the glacier is, how big the snowfield that it's growing in is, therefore how much weight is coming down on it. Slope of the land can also play a role in it. Number of different factors. But generally speaking, we have seen glaciers that can move anywhere from inches in a day to meters in a day. One way we can tell is actually by taking a line of stakes and drilling a line of stakes in across the front of the glacier. Not at the actual front edge of it, but back a little ways. And then just watch those, take the GPS reading on those locations and then come back and measure them and see how far they've moved at what time. And we find that glaciers, alpine glaciers especially, move very much like rivers do. So remember back to the way water was moving in the river channel. We said that the water would move faster in the center of the river because in part because it's further away from the edges. We find the same thing, is that the ice in the center of the glacier moves faster. And it doesn't move uniformly. Because of that faster motion, it causes the ice to move kind of a turbulent form, so it's constantly moving stuff around within it, bringing stuff up to the surface. So if we look at a glacier in a different manner, I'm going to use our longitudinal cross-section again. I'm just going to take out some of the stuff. And you know what? I'm just going to redraw this at a different scale. We take a larger view of the glacier. All right. Longitudinally, we can break up a glacier into two different regions. And I'm just going to kind of arbitrarily draw a line up here for this. Okay. The upper end is the zone of accumulation. This is the point where anything that falls on the glacier is going to become part of the glacier. So this is usually above what we call the snow line for a location. Now, what the snow line is that is the average elevation you have to be at a given longitude, or sorry, given latitude, to have snow remain on the surface of the ground year-round. When you're near the equator, that's somewhere north of 14,000 feet. As you move further north or south of the equator, it lowers substantially. So by the time you get down to about 66 degrees north or south latitude, it's only a few hundred feet, if not less, above sea level. So the zone of accumulation is where basically material is going to be falling and adding to the glacier. So the glacier is accumulating material. The bottom of the glacier, below the snow line, is the zone of wastage. This is where the glacier is losing material. It can be losing it through the process of sublimation, which is basically a process where water turns directly into gas. It could be through melting, where the glacial ice is just melting into water. Or it can actually be through a process called calving, where chunks of the glacier are breaking off. So generally speaking, what this means for us, though, is that we can look at the balance of a glacier based on what's happening with the end of the glacier. And we can tell what balance a glacier is in by what the end of the glacier is doing. So, if the accumulation equals the wastage, then the glacier is going to be in balance. The end of the glacier is not going to appear to move. While the glacier is still internally moving, the end of the glacier appears to be stationary. If, on the other hand, accumulation is less than wastage, so we're melting more material than we're adding, the glacier is going to be in retreat, and we're going to see the end of the glacier move back uphill. We see that with most of the world's glaciers right about now. Then if we have the opposite, where accumulation is greater than wastage, we see the glacier actually begin to advance, and it moves further downhill. So basically, it really comes down to whether or not the glacier is getting enough material to feed itself versus how much it has to be losing because of the temperature climates that it's within in its lower extremes. So let's talk about erosion now with glaciers. They're very, very powerful erosive agents. Glaciers really are, bar none, the greatest mover of sediments on the planet. One glacier can easily move more material than most, if not, about most of the rivers in the world, and some of them combined. It does this because ice simply can hold so much more material. So, generally speaking, they erode the land through abrasion. Okay, so generally, glacial ice freezes chunks within it. These chunks can range from boulders as big as houses to very, very fine-grained material that is literally as fine as powdered sugar or even flour. And in fact, sometimes we refer to it as rock flour. And this material just scrapes against land. So you can think of the edge of the ice like a super sand belt, where it's just sanding away material, just grinding it away time after time after time. So abrasion is one of the major ways that it acts. And we can see this also because the interesting thing is that you have the coarse material with the fine material. For those of you that have done woodworking or any sort of auto body work, or use sandpaper in general, we refer to the roughness of sandpaper as in terms of the grit. And the grit number usually is the number of particles per square inch. So 40 grit sandpaper has 40 particles per square inch. 2,000 grit sandpaper has 2,000 particles per square inch. Basically, the higher the number, the finer the sandpaper, the more likely it is to leave a very smooth, even polished surface. I've used some sandpaper. It goes down to 4,000 grit sandpaper, and it will literally polish wood. Glaciers are at one and the same time have this super rough grit, because again, it can have blocks in it the size of houses, and it has this hyperfine particle material in it. So at the same time, glaciers will actually scratch the land or gouge the land out and polish it at the same time. So it's not unusual to go to some place like New York City in not Times Square, Central Park, and you can actually see there. I believe your book actually has a picture of it. Let's see. That's not Times Square. It's not Central Park, but Figure 1213, which is on page 297 in the current version of the book. Yeah, it shows it pretty good on here. This is a surface that has got glacial striations. Those are the stripes you see coming in this direction, as well as glacial polish. So you had larger chunks that were scraping against and gouging out scratches in the rock, and then you had the finer grained material polishing the surface into a shiny surface. So that's one way glaciers can cause erosion. The other is a little stranger process called plucking. Anybody here, and I know you guys can't respond back to me in this method, but anybody here ever see the movie, I'm drawing a blank, not a Christmas Carol, shoot, I can't remember what it is now. It'll come to me. Anyway, movies where people stick their tongue to a frozen pole outside in the middle of winter, and their tongue gets stuck. Why does your tongue get stuck? Some people say, oh, your tongue freezes to the pole. Well, technically yes and technically no. It's not the tongue that's frozen. It's the saliva on the tongue. So when the tongue hits the pole, the moisture on it begins to freeze. And of course, remember, we talked about this before, that when water freezes, it expands. Well, when it expands, it captures the structures, the lapilli type structures that are on your tongue, your taste buds basically, and it freezes around them. So the only way to come away is, you rip part of your tongue off, the surface of your tongue off. So, but that's a very similar process to what glaciers do. Water can melt into the rocks, it can freeze into the fractures, and then as the glacier moves, it pulls the glacier away. Part of this happens because of the immense pressure the glacier is putting on the ice, on itself. If you take two pieces of ice, wear gloves if you're doing this, please. If you take two pieces of ice and squeeze them together really, really hard to the point where they start dripping, and then release it, odds are the two pieces of ice will stick together because they're going to fuse. What's happening is the pressure you're putting them under is melting the water at the point of contact. And the second you release the pressure, that water refreezes, causing it to lock together. Well, now if you've got something that's frozen onto the glacier like that, and the glacier pulls away, it's going to pluck that material right off the wall. And that's the other way glaciers do their erosion, by plucking. So, there are a number of landforms that are created by glaciers. Normally in class I would try to draw these out, but I don't think I can do it justice in this format with this whiteboard. So, I want to go over them, but I want to refer back to the book on this. So, Again, page 297 in the book. This would be figure 1214. For those of you that have the older version of the book, this is probably going to be about 15 pages back, so try around 229, 230, but somewhere in there. But basically what you're going to want to look for is a series of block diagrams. So in this block diagram, it's showing you a typical mountain range with riverine valleys before the glaciers occurred. In the second block diagram, it's showing you the same system, the same terrain, but now it's been under glaciation for a while. And then the third block diagram is the glaciers have melted away, leaving the erosional features behind. So what are some of these features? Well, some of these features are going to be, one, aretes. These are basically ridges between glacial valleys that, because of the processes that have been going through them, they're sharpened like a knife. They're serrated. So the serrated, sharpened ridges of rock between glacial valleys. There's also horns. Horns form because of another feature that forms during the formation of the glacier. At the head of the glacier, a bowl-like depression is formed that we call a cirque. And this cirque is eroded through primarily plucking. So it plucks back. If you get multiple cirques coming back to back to back, so at least 3 cirques back to back to back, they'll create this pyramidal type of sharp rocky peak that is called a horn. The Matterhorn in Switzerland is technically a horn. So we have that. We also can have what we call the truncated spurs. Normally, when you look at a valley a ridge between valleys, it comes down and it goes all the way down to almost the valley floor and then comes back up. In glacial situations, this gets truncated and becomes literally a sheer cliff. So you get the sheer cliff that's because the glacier cut it off. This is because of the shape a glacier takes. River valleys, if you remember, are V-shaped. Glacial valleys are U-shaped. Get it over there. So V-shaped versus U-shaped. So glaciers, for the same reason that rivers want to be semicircular, glaciers also want to be semicircular. So they tend to create a U-shaped valley when they erode the system. So they're going to cut off the ends of those ridges that would normally come down. So in this upper block diagram, you can see the ridges coming down, but here it's truncated off. They're truncated by the glaciers. Right. This also creates some other issues that once the ice is melted, we can see, such as the hanging valley. So a tributary valley of the glacier going into a larger one may not have dug down as deep, so you get these hanging valleys. It creates some spectacular waterfalls in parts of northern Europe. You can get rock basins, rock steps, which is basically where the glacier may have changed its shape a little bit and its size. You can also get a couple of other features that don't show up in your book, but I want to talk about them real quick. You can get what are called paternoster lakes and tarns. The interesting thing about these is that these are depressions that are in glacial valleys that have been subsequently filled with water, hence the paternoster lake. Generally speaking, though, when you look at a glacial system, the paternoster lakes, let's see, double check here. Okay. Your book calls them rock basin lakes. I like paternoster better. I don't know. But the paternoster lakes are the lakes that you're going to find in the glacial valley. A tarn is a paternoster lake, but it's a paternoster lake in a cirque. So it's just a special name for it is all. Let's see. Oh, Rocher Montagnais. Rocher Montagnais, is actually a erosional feature that is found not by alpine glaciers. Most of what we've talked about so far is associated with alpine glaciers because alpine glaciers leave the most evidence for us, at least in terms of erosional features. But Rocher Montagnais are a feature that are left behind by continental glaciers or ice sheets. And they're actually really interesting because of the shape they take. And they take this shape. They're actually fairly easy to recognize because they look something like this. This would be a Rocher Montagnais. This is basically an outcrop of bedrock that has been streamlined by the flow of the glacier. The glacier went over it this way, so this part of the rock was smoothed into a nice smooth ramp. Down here, the downstream side, this was taken by plucking. So the rock was removed by plucking, creating a sheer cliff. So that's one of the signs of a ice sheet that has gone through an area. Keep in mind, ice sheets can be over a mile thick. So, it could be going over a small mountain or hill that's, maybe a half mile, 3/4 mile thick, and it just bulldozes this thing down into one of these shapes. Now, generally speaking, we can also get a lot of deposition. Since glaciers are so great at grinding material and carrying material, this means they're going to deposit a lot of material. Now, generally speaking, there are two types of material that we have to keep in mind that are made up by a glacier. The first is, both of these can be termed as glacial till or glacial drift. Both of them are termed as glacial drift. But glacial drift is separated into two specific categories of types of material. The first is what we call glacial till, or just till. This is material that deposited straight from the ice. It's not reworked by water, it just was deposited straight by the ice. Okay, so no reworking. The other type of material is what we call stratified drift. This is glacial till that was then reworked by meltwater. So it was worked in a riverine system that derived from the glacier itself. A lot of times the stratified drift is reworked in a braided stream system. So if you remember when we talked about braided stream systems, those are systems where the water is choked with sediment and it's depositing material and picking it up at one and the same time. So generally speaking, most of the formations that we talk about are made out of till. So the big ones that I want to mention to you are the moraines. These are features that are directly deposited by the ice. There's a couple of different types of moraines that we want to be interested in. They're layers or ridges of till. So it's layers or ridges of material directly deposited by the ice. There are lateral moraines and medial moraines. These are moraines that are produced by alpine glaciers, either on the sides of two glaciers. So it's a ridge that forms on the side of the glacier, or sediment that forms on the side of the glacier. Or a medial moraine is where, like a median on a road, but it's where two glaciers come together and the lateral moraines for them become a medial moraine. Now, those are typically associated with alpine glaciers. When we start to look at all glaciers, alpine plus the continental ice sheets, what we see is that we get end moraines. End moraines are ridges, sometimes sinuous, but they're ridges of till that mark the point at where a glacier came to rest. So where the end of the glacier was stationary for a period of time. So think of the glacier like a giant conveyor belt. The end of the glacier, if it's stable, is staying in one spot, but the ice keeps coming down. So it keeps bringing more and more and more material. It just piles up a big ridge. That would be an end moraine. Now, there's a special type of end moraine that demarks the furthest extent southwards in the northern hemisphere or northwards in the southern hemisphere of a glacier, and that is the terminal moraine. The terminal moraine demarks the farthest point the ice actually was able to extend and then sit for a period of time. Then we get recessional end moraines after that. And these are going to be moraines that when the glacier retreats, it stops for a little bit, drops a moraine, retreats again, and so forth and so on. Generally speaking, you don't see end moraines that represent an advance of a glacier. You only see end moraines that represent the retreat of a glacier. We can also have a ground moraine, which is just basically if the glacier is moving back at a steady pace, it's just dropping a thin layer of material down. We can also have drumlins. Drumlins are these smooth, elongated hills that that are like that are kind of shaped like the Rochers Montagnais, but in reverse. The steep end faces the direction the ice came from. The flattened end faces, or the smoothed end faces the direction the ice went. The formation of these is not well understood, but one of the working hypotheses is that this is basically evidence of some sort of moraine system that was then plowed under by the ice. And so it piles up, and then the ice gets over it and smooths it. That's at least the working hypothesis right now. When we look at these landforms created by stratified drift, we're looking at things like outwash plains, which are broad ramps of reworked material. Generally speaking, these will show various types of riverine features, including minor cross bedding, braided channels, graded bedding. So it shows those types of features, but can also show some interesting features that are kind of depositional and kind of not at the same time, and that's kettles. Kettles are pockmark-like depressions in an outwash plain. They form when large chunks of ice fall off, land, and get partially buried by the sediment that's being worked. When the ice is gone, it melts. If it leaves an empty depression, it's just called a kettle. If the depression has water in it, it's called a kettle lake. What's the nickname of Minnesota? The land of 10,000 lakes. Why does Minnesota literally have 10,000 lakes? Because it has 10,000 kettle lakes. So you have all these depressions that were left by chunks of ice that then melted and now have formed these little lakes all over the place. Some other features that we can see, I'm not going to get too much detail into them, are cames, came terraces, and eskers. Eskers I kind of like because they are a form of a sinuous ridge that's formed by a river of meltwater under the ice. Technically, the esker is the tunnel under the ice that's where the river is flowing. If it fills up, it can become a ridge called a moulin. So let's move on to ice ages. Ice ages are an interesting thing that happened to the planet multiple times. Sometimes they get out of control, sometimes they don't. In the last couple million years, we have 4 major ice ages that have been recognized in North America. The Nebraskan, the Kansan, the Iowan, and the Wisconsin. Basically speaking, these are events that are basically named based on where the terminal moraine of that advance is located. During this ice age system, 30% of the surface of the land was covered by ice. Some of it up to or over a mile thick. It began between 2 and 3 million years ago, and most of this happened during what we call the Pleistocene epoch. Now, we have indirect evidence of the glaciers outside of the direct evidence. Some of the direct evidence we have are the moraines, of course. We also have areas where the rocks have been polished. There's almost no soil development. The soils have been scraped off and left somewhere else. We have features called erratics, which are boulders that have been carried by glaciers and deposited. So you have these boulders of material that do not look like anything like the bedrock in the area, that came from hundreds, sometimes thousands of miles away. Then we have the indirect evidence, which is things like changes in the migration of animals and plants, changes in stream courses. The Mississippi River didn't actually used to flow south. It used to flow north, according to research. Rebounding of the land. The ice sitting on the land is a weight. And we haven't talked about this yet, but the crust of the earth will respond to weights put on it. So over time, the ice depresses the earth. When you melt that ice, the earth will slowly rebound back to shape. We actually see this happening around the Great Lakes. In some areas, they're rebounding about an inch a century. We also have noted worldwide changes in sea level, as well as climatic changes that are in the fossil records. Now, what causes glaciation? This is at the start of this, I wanted you to think about this. We're going to go over some of the changes, but at the end, there's something else that I think we're missing that needs to be taken into consideration. So any successful hypothesis that would become a theory that would account for glaciation would have to basically figure out what causes the onset of glacial conditions, as well as the alteration of glacial and interglacial stages that have been documented within the past. So we look at some of the things. Plate tectonics. Big part of what could be part of the picture is plate tectonics. In part because plate tectonics can change the way the continents are configured, which changes ocean circulation. And ocean circulation is the major force for heat redistribution on the planet. If several million years ago, the Isthmus of Panama didn't exist. So the current that flows from the equatorial regions of the Atlantic didn't have a diversion, and then we get moved north and south to form, in the northern hemisphere, the Gulf Stream current, which actually makes New York City warmer than it would be if that current wasn't there. So we can have changes to ocean circulation, which can have major effects on the worldwide climate. Then we also have variations in the Earth's orbit. We call those the Milankovitch cycles. That's basically three factors in the way the Earth's orbit changes over time, or the Earth changes over time. It's not physically, but in the way it behaves in space. So first of these is the shape of the orbit. The orbit of the Earth is not circular. It's not circular. So that's very important, which means that there's one point of the year where we're further away from the sun and one point of the year where we're closer to the sun. This is called the eccentricity of the orbit. Right now, we just passed our closest approach to the sun. We are actually closer to the sun in our orbit during our winter than we are during our summer. So this is why the extremes in the southern hemisphere seem to be so much larger than the extremes in the northern hemisphere. So, but over time, over the course of about 100,000 years, this orbit goes from being more circular to being more oval, and goes back again. So when it becomes more oval, we see larger extremes in the daylight received in one hemisphere versus the other. The angle of the Earth's axis. The Earth's axis is not straight up and down in relationship to what we call the solar plane or the solar ecliptic. This is the plane that's from the equatorial region of the sun. So it would be basically if you took a plane from the equator of the sun and spread it out, the Earth is actually tilted about 23 degrees in relationship to that. And actually the Earth's tilt varies from about 22 degrees to 24.5 degrees back and forth over the course of time. And so that can change the seasons drastically. The more strongly the Earth is tilted, the greater the seasonal variations will be. So the warmer the summers are, but the colder the winters are. The less tilt there is, the less variability there is in the seasons. And then you have the axial wobble, or the precession. The Earth, if we imagine the Earth as a spinning top, and I don't have a ball, that would be better. If we imagine this is the Earth's axis, and it's rotating around like this, well, it turns out, let me turn it this way, this will be better. It turns out it doesn't spin perfectly, but more like I'm doing, it wobbles like this. Sort of like a top. When you see, if you've ever spun a top and it's starting to wind down, it starts to wobble. We call this precession. This happens about every 26,000 years. This precession. So the North Star today was not the North Star 12,000 years ago. It was a completely different star. It will not be the same star in a few thousand years. Wobble changes how the planet is oriented in space in relationship to the other two processes. And so it can create situations where our winter is where instead of our winter being closer to the sun during our winter, closer to the sun during our winter, we could be further away from the sun during our summer and winter, and that can cause changes in the system. Basically, what we're doing is we're playing with the amount of heat energy that's being received by the Earth and changing that. Now, the Milankovitch cycles fit fairly well, but there's still a problem with them in starting a ice age. And that's simple thermodynamics. Because we can't just simply cool the planet down. A lot of people, when asked what causes an ice age, they'll say cooling the planet down. But if we think about this logically, that doesn't make any sense. Because if you cool the planet down, then you decrease the amount of water vapor the atmosphere can hold. If you decrease the amount of water vapor the atmosphere can hold, you decrease the amount of rainfall. These glaciers usually grew in very, very rapid succession. So in some estimates, maybe as short as 1,000 years. That's a lot of snowfall. If you chill the planet, you're not going to get as much snowfall. We actually have to heat the planet. And I know this sounds counterintuitive, but what you have to do is actually heat the equatorial regions of the planet while keeping the polar regions cooler, so you get more of a zonal heating of the Earth, which can be done. The Milankovitch cycles do seem to lend to some of that happening, as well as ocean current situations. So we actually need the equatorial regions to get warmer in order for there to be more water vapor, in order to increase the amount of snowfall precipitation in the colder regions, to therefore be able to grow the glaciers. At least that's my working hypothesis right now. So, but with that, I'm going to end this. We're at about 49 minutes. So this was chapter 12. I'm also going to get chapter 13 up here shortly. I'm going to rest my throat for a little bit before I do that. And I'll talk to you guys later.